In this section, we will discuss conditional distributions, which is a sort of vast generalization of Fubini theorem in calculus and real analysis. So we'll begin with some motivation and discussion of the main result and some example, and then a little bit later we will prove the main result of this section. So as a motivation, let's recall that in calculus, when we integrate a function on the plane with respect to the area measure, we can integrate it one coordinate at a time. So the Fubini theorem is that we can integrate this function with respect to, let's say, the second coordinate first, and then we integrate that result with respect to the first coordinate x. And then in real analysis, there is, of course, a generalization of this to product spaces with product measures. So in particular, if we consider a measurable function f on a product of some measurable space x with the sigma algebra x, and another measurable space y with the sigma algebra y, then given some measures p and q on these two spaces, we can define a product measure, so p times q, and we can define integration with respect to this product measure, and we also have the Fubini theorem. Now, in this case, let me just focus on the case of probability measures. So here, I will assume that these p and q are probability measures. And then the Fubini theorem in this case is, of course, the statement similar to the above, that the integral of a measurable function f on this product space with respect to this product measure mu can be written as a double integral, where you integrate this function with respect to the second coordinate, and then you integrate the result with respect to the first coordinate. And of course, if you recall, the product measure is defined by defining it first on rectangles, then extending it to all measurable sets on the product sigma algebra, and then from there, once you define the measure, you prove this Fubini theorem. Now, depending on the real analysis class, sometimes a more general situation can be considered. So let's mention a bit more general setup, where instead of defining a product measure, you consider some transition kernel, and you define the measure on the product space with respect to this transition kernel. The definition of the transition kernel is basically it replaces this measure q on the product space on the second coordinate by a family of measures q that also depends on the first coordinate x. So namely, a transition kernel is a function that depends on the first coordinate x, and it depends on the set, on a measurable set on the second coordinate. Okay, so for any x in x and any measurable set in the sigma algebra y on the second space. And the transition kernel is any function of this form which satisfies the following two conditions. That first of all, for any x, when you view this q as a function of a set, it's a probability measure on the sigma algebra y. And the second condition is that for every measurable set in y, when you view q as a function of x, so for a fixed set A, when you view it as a function on the first coordinate x, it is a measurable function on that space. Okay, with respect to the sigma algebra x. And given this transition kernel, you can generalize the definition of this measure mu on the product space as well as Fubini theorem as follows. Namely, when you consider this product space with coordinate x and coordinate y, and then you take some measurable rectangle on this space with side b on the first coordinate and side a on the second coordinate. Well, first of all, on the first coordinate x, we suppose that we have some probability measure p, and then for any fixed point x on the first coordinate, on that slice, we consider, instead of the fixed measure q, we consider this measure q, this probability measure q given by this transition kernel for this given x. Okay, and then we define measure mu of this rectangle with sides b and a by integrating over x in this first side b of the measure q of a, only now it depends on x. And so our assumption that this is a measurable function in x means that you can integrate it with respect to this probability measure p on the first coordinate, and you will get some well-defined quantity mu. And so once you define this measure on the rectangle, the rest is exactly the same as in the case of the product measure p times q. So if you go through the proof in real analysis, if you only saw the case of the product measure, you can show that you can extend this to the probability measure on the whole space, on the product space, and then you also get a generalization of the Fubini theorem, which in this case looks as follows. Okay, namely, once you define this measure mu, when you integrate a measurable function f on the product space with respect to this measure mu, you can first integrate with respect to the second coordinate y, right, with respect to this measure q, which now depends on x. And our assumption in the transition kernel that this function is measurable with respect to x, you can also show that the result, this first integral, will be measurable in x, so you can integrate with respect to measure p on the first coordinate after that. And so one gets this slight generalization of the product space construction, where the second measure is replaced by the transition kernel depending on the first coordinate. So I'm not going to go over any details of this particular generalization or this construction, and simply assume that once we define the measure on the measurable rectangles of the form b times a, then we know how to extend this to a measure on the whole product space, and then one can derive this generalization of the Fubini theorem. And so the main topic of this section is some sort of reverse of this statement that I described here, given this transition kernel. Okay, namely, if we consider a product space and some probability measure mu on that space, can we construct this transition kernel Q so we have such Fubini theorem? So instead of starting with the transition kernel, here we want to start with arbitrary probability measure mu on the product space and ask whether this Q can be constructed. Okay, and instead of transition kernel, in this kind of reverse setup, this Q will be called conditional distribution or conditional probability, or sometimes it's also called regular conditional probability. Okay, so once again, given a probability measure mu on the product space or this product sigma algebra, of course, probability on the first coordinate, it's automatically determined by this mu, right? Because probability of any measurable set on the first coordinate, if you assume this Fubini representation, it just means that the rectangle that you should take has the second side without any constraint, right? So the second side should be the whole space Y. And so the probability p, the marginal on the first coordinate, it's automatically determined. And then the main question here is, can we define this transition kernel Q? Okay, such that the measure mu corresponds to exactly the above construction, and the Fubini theorem I mentioned above holds. Okay, and as I said, in this kind of reverse setup, this Q will be called regular conditional probability rather than transition kernel. Okay, and sometimes you can omit the word regular and just call it conditional probability. Okay, and the answer to this question, which will be the main result of this section, is that indeed you can construct such transition kernel in the case when this second space Y is regular. And regular means that it's a complete separable metric space. And of course, in this case, the sigma algebra is just the Borel sigma algebra. And before I state this main result, let me discuss what the main difficulty is, and also discuss that there is actually a natural candidate for this transition kernel Q, because we already have this construction of conditional expectation. And of course, probability is expectation of indicator, so conditional probability will naturally be conditional expectation of indicator. Again, let me say that we are looking at this product space with the product sigma algebra and some probability measure mu on it. So we have some probability space of this form. And then, to avoid some confusion, let me define the coordinates on this space as function of the point xy. So I'll denote by f the second coordinate y, and by h the first coordinate x. And as I said, the natural choice for this transition kernel, at least for a fixed set A in this sigma algebra y on the second coordinate, will be, as I said, just the conditional expectation of the indicator. So it will be conditional expectation of the indicator that the second coordinate y, or I denote it by f here, belongs to this measurable set A conditionally on the first coordinate, or conditionally on the sigma algebra generated by this first coordinate, which I denoted by function h. And of course, we know that this conditional expectation, by definition of conditional expectation, it will be measurable with respect to the sigma algebra, so it's sigma h measurable. And of course, the sigma algebra generated by the first coordinate just consists of rectangles of the form b times y. So you have no constraint on the second coordinate for all measurable sets on the first coordinate, so in the sigma algebra x. And of course, it's easy to see that a function on the product space, so a function of two coordinate x and y, which is measurable with respect to the first coordinate, it must be a function of the first coordinate. Right? So indeed, I denoted this on the left-hand side as a function that depends only on x, and it is indeed a function of x. Because if for a fixed x, it would not be a constant depending on y, then on that particular slice, you could have a preimage which is not of this form, right? Which is not given by a rectangle with no constraint on the second coordinate. Okay, and the reason why this is the natural choice, at least for a fixed set A, this is a natural choice of this transition kernel that we are looking for, is because we do have automatically Fubini theorem for rectangles, just like we want. So with this definition, we can check immediately the Fubini representation for rectangles. Because if we integrate, so we want to integrate this transition kernel Q over some set B with respect to this marginal on X, right? And of course, integrating with respect to X is just taking expectation on this product space. So the fact that we are integrating over B just means that we should put indicator that the first coordinate H belongs to B times, so we defined this transition as this conditional expectation of the indicator that the second coordinate belongs to A given the sigma algebra generated by the first coordinate. Right, and so this first indicator, it's of course H measurable, and by the definition of conditional expectation given sigma algebra generated by H, this average over the set B should be the same as the average, the unconditional expectation over the set B of this indicator that F belongs to A. Okay, but this is of course just a probability that we have on our product space, so it's the measure mu exactly of this rectangle B on the first coordinate and A on the second coordinate. And if you recall, in the definition of the transition kernel, that's exactly the definition of the measure mu on the rectangle. So the construction in this case of this function qx of A, it does match at least for a fixed set A. Okay, but then of course, what is the difficulty in this case? Why we cannot just define the transition kernel the way we did here for all sets A and automatically claim that this gives us the transition kernel that we are looking for? Okay, well, the difficulty here is as follows. Namely, the transition kernel should be a probability measure for all x, right? And if we look at this question, is this Q viewed as a function of the set of measurable sets? Is this really a probability measure for all x? Right, that's a requirement. Well, for example, if we take Q of some disjoint union of measurable sets, so let's say we have a union of some measurable sets which are disjoint. Now, by the definition, we define this as conditional expectation of this indicator of this disjoint union, which is of course, because these sets are disjoint, is just a sum of indicators of these sets, and we take conditional expectation given the first coordinate, which we denoted by H. Now, by the properties of conditional expectation, of course, this will be equal to the sum of conditional expectations, which again, if for each of these sets we define this conditional expectation as this transition kernel Qx of An, then it looks like we get the countable additivity that we want for probability measure. However, the problem here is that conditional expectations are defined up to some set of measure 0. So in particular, this linearity of conditional expectation is only true almost surely. So there could be exceptional set of points where this equality is violated, right? It's of measure 0, but still for some x's this might not be equality. So in other words, there exists this exceptional set of measure 0 where this equality can be violated. Of course, the problem here is that the exceptional set can depend on the choice of these sets. And of course, there are uncountably many ways you can take, for example, these disjoint unions, right? So we have uncountably many sets in our sigma algebra, typically. So these types of exceptional sets, if we only had countably many of them, their union would still be just an exceptional set of measure 0, but in general we cannot simply define this transition kernel as a conditional expectation for all sets and automatically assume that everything is fine. As a result, there will be some work to do to prove this main result, so let me just state what this main result will be in this product space setting that we are discussing here. In fact, our main result will be a little bit more general and it will be stated in a more abstract form, but in this particular setting of a product space case, we will show that if the second coordinate y is regular, so in other words, separable complete metric space with its Borel sigma algebra, then this transition kernel QXA exists, okay, such that you do have a representation for this measure mu that we started with via Fubini theorem. Okay, so in other words, for all integrable functions on this product space with respect to this measure mu, the integral of f with respect to mu can be written as this double integral, okay, where first you integrate with respect to this transition kernel on the second coordinate and then you integrate with respect to the marginal p on the first coordinate. And let me just mention that sometimes this transition kernel is denoted as follows. So, okay, this can be often denoted as mu dy given x. And when we state this more general abstract form of this theorem, we will also give a statement about the uniqueness of this transition kernel or regular conditional probability. But before we get to that main result and its proof, let's give one example how this theorem can be used, and this is the so-called disintegration theorem. Well, namely, let's again consider a product space where here, for convenience, I'm actually flipping the coordinate x and y, and I'm putting this regular space on the first coordinate in this graph. Then let's consider some measurable function from y to x. Okay, so let's denote this function by pi. So pi from y to x will be some measurable function. And we also consider some probability measure nu on the first coordinate y. And then we will denote by mu the image of this measure by this map. So mu will be just this measure nu pushed forward by this function, measurable function pi. And also let's consider the probability measure p on the product space corresponding to this graph. So in other words, it's this measure nu on the first coordinate pushed to the product space by this map where y goes to the point on the graph. So into the point y, pi of y. And then let's also consider a measurable function f on this product space x times y. And then suppose that we consider the integral of the following form. So the integral on y of this function f, which depends on y through coordinate y and also explicitly through this function pi that maps to this intermediate space x, right? And we integrate it with respect to this probability measure nu on the space y. So in this starting integral, the space x is implicit, right? It's just a space where this function pi is mapped. And suppose that we want to fix for a second this function pi and integrate first in the coordinate y. Right? This disintegration theorem that we will now write down it's just an immediate consequence of the above theorem, because here I assume that y is regular, and as a result we know that this transition kernel exists. So to write down the theorem, we have to first represent this integral as an integral on the product space, right? And that's just by the definition of this measure p. By the change of variables formula, you can of course view this as an integral of the function f of x and y with respect to this image measure p defined on the product space. This is just a change of variable formula. But once we wrote it like this on the product space, and we know that the second coordinate y is regular, the main theorem that we are going to prove will show that this can be written as a double integral, where first you fix x and you integrate with some transition kernel which does exist. So there is some measure q for a fixed x on the second coordinate y, and once you integrate with respect to this, then you integrate with respect to the marginal on x, which here we denoted by mu. And so now if we omit this intermediate step, this equality going directly from the left-hand side to the right-hand side is exactly called the disintegration theorem. Right? And the meaning of this theorem is that when you start with an integral on this space y on the left-hand side, and you want to fix this function pi first, right, you can do this, and there will be some measure that depends on x, so that you can integrate with respect to that measure on the second coordinate y, right? So you can fix this pi of y first, right, and integrate with respect to the second coordinate. Now there is some additional information on this transition kernel that may be useful, and it's often also part of this disintegration theorem. So first, let me assume that our space x is also nice, and in particular, let's suppose that the particular function, this f of x and y, given by the indicator that x is equal to pi of y, is measurable on the product space. Okay, so this is not always the case. If the space x is not nice, this might not be true. But if a space x is, for example, also separable metric space, then this indicator will also be measurable. And then if you apply the above statement to this indicator, you will see that on the left-hand side, you just have an indicator that pi of y equals to pi of y, right? So on the left-hand side, you're integrating indicator that pi of y equals to pi of y with respect to this measure nu. So this will be just equal to 1. And on the right-hand side, when you integrate the indicator with respect to this transition kernel first, well, the integral of the indicator is just a probability, so it will be q of x of the set that you integrate over. So all points y where x is equal to pi of y. And then you integrate this with respect to the marginal on x. Okay, and then if you notice that this is a probability, so this q for any set is between 0 and 1. And you also integrate it with respect to a probability measure mu. And the result is equal to 1. Well, that tells you that you are integrating 1 almost surely, right? So from this particular example with an indicator, you can see that for almost all x, or for mu almost all x, you must have that the measure q for this fixed x of the set y where x is equal to pi of y is equal to 1. So in other words, this transition kernel is concentrated on the level set of our function pi. Right? So Qx as a measure is concentrated on this level set where the function pi of y is equal to x. Okay, so if we go back to this graph here and we say that we want to fix this function pi of y, right? So we take some point x here and we fix the level with this function here. And then the measure q on this slice, so we are defining this transition kernel q on that slice, will be concentrated on the level set, right, exactly on these points where the function pi takes this value. Okay, which is kind of natural, but here in this particular statement it does assume that the metric space x or the space x is also nice, right? The indicator that we integrated here is a measurable function. Now, if the space is not nice or you don't make any assumption on the space x, sometimes this second statement about these layers where the transition kernel is concentrated has to be rephrased a little bit, and so one typically gets the following a little bit more general statement. Now, I'm not going to prove this here. It's basically one line proof in the notes, but I'll just mention the reason why it's written that way, right? So if the space is not nice and you cannot consider the indicator above, instead you have to consider some test functions. So for example, if you fix some measurable function h on this coordinate x, then one can show that for almost all x, or for mu almost all x, the measure q for this fixed x will be concentrated on y, where not x is equal to pi of y, but you have to pass through this test function. So h of x is equal to h of pi of y, right? So that set has a probability 1. Now, of course, once you have this kind of statement for one function, you can also take countably many h if you like. Right? This statement will still be true for countably many h for almost all x. And in particular, one of the exercises in this section asks to use this kind of more general representation to show the above statement for a nice space, like a separable space, that this actually implies that the measure q concentrates on the level where x is equal to pi of y. But the main statement in this example of disintegration theorem is just a direct application of this main result, the existence of this transition kernel. And before we move to this more general abstract statement of the main result and also prove it, let me just mention that this is one of those sections where perhaps exercises are more important than the results themselves. So it's very important here to take a look at essentially as many exercises as possible. And final comment here is that since this main result is obviously a vast generalization of the Fubini theorem in calculus, and one cannot overstate the importance and the usefulness of the Fubini theorem in calculus, in many chapters we will see a lot of applications of this later on. There will be, of course, many uses of this Fubini theorem in various chapters. And next we will state and prove the main result in this section, which will look a little bit more general than the theorem that I stated above.